Continuing 3.5 on graphing using transformations, let's look at exploration number 3. So previously what we saw was our parent function. We first had the square function, and we would evaluate the function in our transformation, and then we added 2 and we saw a shift up. Of course, if we had subtracted 2, do you suppose it would have shifted down 2 units? Yes, exactly. That's what would have happened. And in the second exploration, where we saw the shift to the horizontal shift, we saw the addition of 1 happening inside the absolute value bars, which indicated that this was going to be horizontal. But remember, it was +1 and it went to the left. So the horizontal shift is a little tricky. If it had been -1, absolute value of x minus 1, our shift would have gone to the right. So now let's look what happens when we start with a parent function such as the square function. And now instead of adding or subtracting anything, we're going to multiply. But again, notice the first thing you do is raise to the power, right? You would evaluate by substituting a number in for x, then you would square before you multiplied. Square before you multiplied. So this transformation is taking place outside of the original function. We do the original function, then multiply by 2. Evaluate the original function, then multiply by half. So this should be similar to what we saw outside the function in exploration number 1, where we squared x, then added 2. Okay, so we're supposed to sketch all 3 of these. Now the f of x, we should by now be used to what that looks like, right? The values I've been choosing are -2, -1, 0, 1, and 2, because they're just the smallest integers here and will fit on my provided graph. So -2 squared, so if I go to -2 and square it, I get +4. If I go to -1 and square it, I get +1. 0 squared is 0, 1 squared is 1, and 2 squared is 4. So here is that original square function, the parent function here. All right, that one's f of x. All right, so now let's see what we get for g of x, which they say is 2x squared. So let's make a table for that one. X and g of x. Okay, and let's choose those same values, -2, -1, 0, 1, and 2. So now we're going to square -2 and get +4, and then multiply by 2 and get 8. Square -1, get +1, multiply by 2 and get 2. Of course, this is 0, then this would be 2, and 2 squared is 4 times 2 is 8. So now let's see where g of x is. -2, +8, -1, +2, 0, 0, 1, 2, and 2, 8. So we're still at 0, 0, but notice our parabola is now is inside the one that we had before. It's actually gotten skinnier. It is being, if you can imagine, being stretched, pulled from the top and made to be skinnier. So let's see what happens for our h of x when we evaluate the x squared and then multiply by a half using the same values. Okay, -2 squared is 4, half of 4 is 2, -1 squared is 1, 1 times a half is 1/2, 0, 1/2, and 2. Okay, -2, +2, -1, 1/2, 0, 0, 1, 1/2, and 2, +2. So now notice that we are on the outside of our original parent function. Here's g of x was this one. So our parabola is actually opened up more. Instead of getting thinner, it's gotten wider, right? So this is what we're seeing with our, these are what we call vertical stretches and compressions. So what we would call this one would be a stretch by a factor of 2. I didn't really plan for that too well, did I? This one's a stretch by a factor of 2. This one's a compression. If you can imagine that original square function being compressed, it would make those branches go out. Compression by a factor of 1/2. And which direction is this in? It's vertical. We're vertically stretching or vertically compressing. So let's put that. Vertical stretch by a factor of 2, vertical compression, vertically pushing down on it, making those branches go out.